All right, everybody. So in this section, we are going to do section 1.3, which is average rates of change. We're going to start using this section to help us develop the idea of what derivatives are over the next few videos. So that's kind of the main purpose here. All right, so average rate of change. So I hate just kind of jumping into a mathematical definition here. So I'm going to try to give it a very basic kind of a real world example here. If you were to travel 150 miles in 3 hours, then you could calculate that your average rate of change in distance per unit of time, or miles per hour, is 50 miles per hour. So you've probably been driving your car at some point. If you drove 150 miles in 3 hours, you go 50 miles an hour on average. Pretty easy to figure that out. If you were to glance at your speedometer at any one point during this trip, you might see that you were actually traveling at some point at a rate of 55 miles per hour. But on average, you didn't go 55 miles per hour. That rate that you're going at that specific time is called your instantaneous rate of change, which we will get a little bit more into probably in the next section. So, for example, to make you think this way as well, state the average rate of change for each of the following. Be sure to indicate units. So if Jan rode a bicycle for 30 miles in 3 hours, what would be your average rate of change? Well, if you traveled 30 miles in 3 hours, you would simplify your fraction. 30 divided by 3 is 10, and that would be you average 10 miles per hour. Number 4, if it snowed 12 inches between midnight and 8 a.m., well, if it snowed 12 inches, the time here, so midnight to 8 a.m. would be 8 hours. If you simplify 12 divided by 8, those both share a 4 in common, so that would be 3/2 inches per hour. If the homework allows you to do decimals, you could put 1.5, but if it doesn't, you may have to leave it in fraction form. And that's pretty much what average rate of change is. Now we're going to do some more like with functions and stuff, but that mindset is what we're going to focus on for this lecture. So let's apply average rate of change to a more mathematical approach now. So if you want to calculate the average rate of change of y with respect to x, it is the following ratio. You can do it one of two ways. You can represent it as the formula y2 minus y1 over x2 minus x1, or you can think of it in the form f of x2 minus f of x1 over x2 minus x1. As long as x1 and x2 are not the same thing, you can use either one of these formulas. Now, y1 and y2 can be the same thing. It doesn't happen very often, but it is an option, right? So essentially what you're doing here is you are trying to take 2 points on a graph, let's say P and Q. And while the curve is actually this pink curve that we would draw, we're trying to calculate the average rate of change, which actually just ends up being the slope of the line between those 2 points. So you're calculating the change in y divided by the change in x. That is just the definition of slope that we went over, I think, the very first problem of the first video. So let's do that. So if f of x is equal to x cubed, I want you to find the average rate of change between the following two numbers. So we're going to do the same function with 3 different intervals. So for all of these, we are since they gave us f of x, I'm actually going to use that second formula, which was f of x2 minus f of x1 divided by x2 minus x1. So on part A, if the two values are 1 and 4, calculate your average rate of change. So if I were to plug my bigger x value in first, that would be f of 4 minus f of 1 over 4 minus 1. So either by hand or using your calculator, you're going to plug 4 into the original problem. So 4 cubed would be 64 minus, and then 1 cubed would be 1, divided by 4 minus 1, which is 3. So this would be 63 divided by 3, and if you use your calculator to calculate that, you will get an answer of 21. Now on your homework, you'll see very similarly, I don't want you to change the function on some of these. I just want you to change the interval and see how much your answer is affected. So what if I change the second number to 2? Well, then my formula would become f of 2 minus f of 1 over 2 minus 1. Now, the only number I don't have here is the f of 2. So if I plug 2 into the original problem, 2 cubed is 8. F of 1 is still 1 over 2 minus 1, which is 1. That would be 7 over 1 and would give us an average rate of change of 7. You can even do this with decimals. You might have to use your calculator a little bit, but we can still do the same thing. So if I change my second number to 1.2 this time, my formula now becomes f of 1.2 minus f of 1 over 1.2 minus 1. Now, I got to find f of 1.2. So in my calculator, I'm going to do 1.2 cubed, which is 1.728, minus f of 1 is still 1, and then 1.2 minus 1 is 0.2. Subtracting the numbers on top, you should get 0.728 over 0.2. And if I type this into my calculator, you get an average rate of change of 3.64. And in all honesty, that's about what average rate of change is. It's just calculating the slope of the line between these 2 points on the graph. The more spread out they are, sometimes that means it's a bigger average rate of change. In this example, the closer the numbers got together, the smaller the average rate of change became. So that leads me to the next part. Once again, this section and the next section are all about developing a big idea in calculus. So definition, the average rate of change of f of x with respect to x is also called the difference quotient. And if you took college algebra here at Mississippi State, we do teach the idea of the difference quotient. This formula might look familiar to a lot of you. It is given by the following. It is f of x plus h minus f of x all divided by h, where h cannot be 0. Now you'll notice down here at the bottom, we're not actually doing anything differently here. You're still going to have the 2 points on the graph, and you're trying to calculate the slope between the lines. The only thing we do different here is we label the points a little bit differently. So we call the first point x f of x, and we find the second point to be x plus h f of x plus h. Because what we're going to end up doing here, and then this may be on the next slide, and I may be jumping the gun, but that's okay. What eventually we're going to do is once we get this difference quotient idea down, we are going to take this second point and we are going to slowly move it towards the first point and make this distance very small. So this h value right here, this distance between left and right of the points, we're going to end up making this h value become very, very small, or that's the ultimate goal. All right, so let's kind of see that. So you can see I kind of jumped the gun a bit, but that's okay. What I want you to do on these next couple of problems is I want you to find the simplified difference quotient and then complete the table for the given function. So I'll come back to the table in just a second. Let's focus on the difference quotient. So the formula for the difference quotient is f of x plus h minus f of x all over h. So if the first problem that I want to do is f of x equals 5x minus 2, I'm going to substitute everything into my problem. So for f of x plus h, what I'm going to do is I'm going to replace the x in the original problem with just an x plus h. You're substituting that into the function. You're going to subtract from that the original function, which is 5x minus 2. And you're going to divide the entire thing by h. And your job here is just to simplify this as far as you can. So here we go. If I distribute the 5, that is 5x plus 5h minus 2. If I distribute the negative to both terms, that is minus 5x plus 2. all divided by h. In the numerator, I can see that these 5x's cancel and these 2's cancel to give me a ratio of 5h divided by h, which is the value of 5. So that is your simplified difference quotient. Now here's where this actually comes out to be very nice. Over here, the table wants you to take that difference quotient and plug in x equals 4 and then variate the h values. But here's the good news. There are no x's or h's in this difference quotient. So you can't plug any of these numbers in. All that means for your table is that every difference quotient value at every single combination will always be 5. And what you probably notice here, or if you don't, I'm going to point it out to you. This 5, if you look back at the original problem, is actually the slope of the original linear function. Slope is consistent everywhere, so that's why our difference quotient value doesn't change. Now that's only true for a line. When you move to other kinds of functions, you're going to have a varying difference quotient value, which we're going to see on the next slide. So here we go. Let's do one that's not a linear function. So if f of x is 2x squared minus x, I want you to once again calculate the difference quotient. So let me put that formula back up here again. F of x plus h minus f of x all divided by h. So let's simplify that and then we'll come back to the chart. So f of x plus h, I'm going to take the original function and I'm going to plug x plus h into both x's here. I am then going to subtract from this the original f of x function, so 2x squared minus x, and then divide all of this by h. This one does take a little bit more cleaning up, but we will get through it. In order to square x plus h, I'm probably going to have to rewrite this as x plus h times x plus h. And I'll do that on the next slide, or next line, sorry. Over here, I'm going to go ahead and distribute these negatives through, which would be minus x minus h minus 2x squared plus x all over h. And along the way, what I will usually do is that if I notice something cancels, I'm going to go ahead and do that. So it's one less thing I have to worry about. All right, so bring down my 2. You need to FOIL x plus h times itself, which would give you x squared for your first, xh for your outer, xh for your inner, and h squared for your last. Bring down the minus h and the minus 2x squared. All of this is divided by h. Distribute the 2 through. Excuse me. That'd be 2x squared plus 2xh plus 2xh plus 2h squared. Apologize for this. Minus h minus 2x squared. All of this over h. And I will notice 2 things happen here. Number 1, 2x squared minus 2x squared cancels. And also you can combine these 2xh's. So this would be 4xh plus 2h squared minus h divided by h. And the last thing that I notice here is that everything shares an h in common, so I can cancel one h out of everything. This h cancels, this h cancels, one of those h's cancels, and that h cancels to be a 1. So your simplified difference quotient would be 4x plus 2h minus 1. Now back over to my chart. The chart says we want to let x be 4 everywhere. So actually, since x equals 4 doesn't change, I'm going to go ahead and plug x equals 4 in. 4 times 4 would be 16 plus 2h minus 1, which simplifies into 15 plus 2h. And then using my calculator or doing basic arithmetic, I'm going to take all of these h values and plug them into here. So starting with 2, if I plug 2 into this difference quotient, I get 19. If I plug 1 in, I get 17. If you plug 0.1 in, you get 15.2. And if you plug 0.01 in, you should get 15.02. And what you will notice is that as your H value gets smaller and smaller, the value of the difference quotient should be getting close to a certain number that we're going to talk about what it is in the next section. So looking at this, it looks like that number is 15. We'll talk about what that number 15 actually is in the next section. All right, so we did average rate of change from a function. Let's actually do average rate of change from a graph. So I want you to use the graph on the right to estimate the average rate of change of the percentage of new employees. So we're going to do 3 different intervals here. We're going to go from 2008 to 2010, 2010 to 2014, and finally 2014 to 2016. So in this one, when you are calculating your rates of change, on the bottom, that's going to be the years that they gave you. Now, we're always going to do the biggest one minus the smallest one. So 2010 minus 2008. On the top, you need to pull the values off the chart. So from 2010, looks like your number is going to be about 2.0. And in 2008, we're just going to approximate here. That looks like it's about 3.2. So getting your calculator out, that should be negative 1.2 divided by 2, which is going to end up being negative 0.6. So when you look back at the graph, that kind of makes sense. It looks like your average rate of change was a negative 0.6 decrease, and that makes sense because your graph is going down between those 2 red circles. How about from 2010 to 2014? So once again, making my graph out. On the bottom, I'm going to do 2014 minus 2010. So if I go to 2014, that's going to be, looks like at about 1.25 minus, and if I go back over here to 2000 and, oops, wrong spot. If I go back over here to 2010, we already found that one to be 2.0. Well, working that out, you should end up having negative 0.75 divided by 4. And if I type that into my calculator, you get an average rate of change of negative 0.1875. And once again, that makes sense because from 2010 to 2014, you took a decrease as you went down. All right, and then to show you how an increase would look, what about 2014 to 2016? Well, on the bottom, you would subtract your years. So 2016 to 2014. 2016 is way up here. So in 2016, you had about, I would say, a 2.8%. Minus the 2014, we used the 1.25, so I'll use that again. If you subtract those, that's going to be 1.55 over 2. And if you number crunch that, make sure I get the right numbers here, you should get 0.775% rate of change. And that makes sense that it's positive because you took a big increase between 2014 and 16. So that would be your average rate of change. All right, and then a couple more here. So trying to, once again, a few word problems here at the end. The amount of money AFT in a savings account that pays 6% interest compounded quarterly for T years when an initial investment of $2,000 is made is given by the following function. AFT is 2,000 times 1.015 raised to the 4t. So we're going to calculate the average rate of change, it looks like, between keeping the money in for 3 years to 5 years, based on the numbers I see. So first thing you want to do is you want to find A of 3. So I'm going to plug 3 into this function. That would be 2,000 times 1.015 raised to the 4 times 3. And so pardon me if I gotta type all this stuff out in my calculator. You should get an answer of 23.91, and we're doing money here, so we're going to call this 24 cents. So you have almost $2,400 in your savings account after 3 years. Well, how much does it change when you go to your 5th year? So I'm going to change this to the same function, but instead of doing 4 times 3, we are now going to do 4 times 5. So let's see, let me type this in really quick. And after 5 years, you should have $2,693.71. So obviously the money went up. So I know my average rate of change is going to be positive, but let's see on average, how much money are you making each year between these two increments? So next thing you would do is you would subtract the two numbers. So 2693.71 minus 2391.24 will give us a difference of $302.47. So that's how much money you made over a 2-year span. But to get the average, you have to divide by the two numbers. So I would take the 302.47 divided by 2, and that will give you $151.24 if you do your rounding. And when it says interpret this value, this pretty much means that between the 3rd year of keeping your money in this savings account and the 5th year of keeping your money in this savings account, you made on average $151.24 a year. All right, and then one more to end this section off. Let's suppose that in T hours, a truck travels S of T miles defined by S of T equals 40T to the 1.2. I want you to find the average rate of change of distance with respect to time as T changes from T1 equals 2 to T2 equals 5. All right, so average rate of change between 2 and 5. Based on the formula we just did and given us the numbers and the functions, your average rate of change is going to be S of 5 minus S of 2 over 5 minus 2. I'm going to plug the 5 into the original problem. I'm going to plug the 2 into the original problem and subtract those and then divide it by 5 minus 2. Now, without a calculator, I know that 5 minus 2 is 3. I'm going to use a calculator to plug these two numbers into the original problem. So if I do 40 times 5 raised to the 1.2, I should get 275.95. Right? For plugging 2 in, if I do 40 times 2 raised to the 1.2, you should get 91.90. Subtracting these two numbers on top will give me 184.05 divided by 3, which then simplifies into 61.35. So on average, it looks like you were traveling about 61.35 miles per hour between the 2nd hour and the 5th hour. That ends section 1.3, which was average rate of change. So a little bit different concept than the limit stuff we were doing. In the next section, I'm actually going to bring limits back and bring back the difference quotient. And we're going to define one of the most popular functions or rules that we will use in this class.